Have you ever wished for an AI assistant that could just, handle it? I'm talking about the complex, multi-step stuff on your computer without getting lost or making some silly mistake along the way. Well, a new research paper might have just cracked the code on this. So let's get into it and see how they're making AI agents way, way more reliable.
You've been there, right? We all have. You give an AI what seems like a totally straightforward task, and halfway through, it just completely goes off the rails. It's a super common frustration, and it's really the core problem this research is trying to solve. Why are these agents so fragile when things get even a little bit complicated? So here's the thing, it's like death by a thousand cuts. For any long task, one tiny mistake, like clicking the wrong button, can just snowball. The agent doesn't immediately know it messed up, so it keeps going down this broken path. Then you throw in random pop-ups or a button that isn't where it was yesterday, and you get this huge variance. The agent might get it right once and then fail spectacularly the next 9 times.
So the researchers asked a really simple but kind of brilliant question. If a single agent is so unreliable, what if we just use more of them? This is the whole idea behind what they call wide scaling. Instead of putting all your eggs in one basket, you just let a whole bunch of agents try to solve the problem at the same time.
And this really shows the shift in thinking, doesn't it? The old way with a single agent, it's like a high-wire act with no safety net. One little slip and the whole thing is over. Wide scaling, on the other hand, is like sending 10 acrobats across the wire at once. You just dramatically increase the odds that at least one of them is going to stick the landing. It might sound like a brute force approach, but it's super effective at making the whole system more robust. Okay, so that brings us to the next big problem, right? You run 10 attempts in parallel, great, but now you've got 10 different results. Some are probably total failures. A few might be kind of close, and hopefully one of them is perfect. So how do you automatically and reliably pick the winner out of that crowd?
And that is where their secret sauce comes in. It's a framework they call behavior best of n, or just bBoN for short. This is the really clever solution to that exact selection problem, a whole new way to figure out what an AI agent actually did. The real innovation here is this thing called a behavior narrative. Now think about it like this. Instead of trying to analyze a confusing video recording of the agent's screen, the system just creates a simple text-based story of what happened. Something like, attempt 1, clicked file, clicked save, task failed. But for another attempt, it might say, attempt 2, clicked file, clicked save as, file successfully saved. It just filters out all that visual noise and makes it dead simple to see which attempt actually got the job done.
So this is the whole process laid out, and it's actually pretty elegant. First, you generate all those parallel attempts. They call them rollouts. Second, each of those complicated rollouts gets boiled down into that simple behavior narrative we just talked about. And finally, you just hand all those text-based stories to a powerful AI judge. And because it's just reading simple text, not watching a bunch of videos, the judge can pick the winner super fast and super accurately. It's just a really smart and scalable system. Okay, the theory is cool, but what about the results? This is where it gets really, really impressive. Let's take a look at the payoff and see how much of a difference this whole bBoN method actually makes.
On a pretty tough benchmark called OSWorld, which tests these agents on real-world computer tasks, this new method hit a 69.9% success rate. And to put that number into perspective, that is a massive 10% absolute jump over the previous state-of-the-art. I mean, in AI research, getting that kind of improvement on a major benchmark, that's a huge deal. This chart really tells the whole story. You can see the previous best was kind of stuck around 60%. The bBoN method just vaults it all the way up to nearly 70%. And look how close that is to the human baseline of 72%. They have almost completely closed the gap. We're talking near human reliability on these kinds of tasks. It's also really interesting to see where that huge gain came from. So the team did build a better base agent, and that accounts for about 35% of the jump. But the vast majority of it, a full 65% of that performance leap, came directly from using the bBoN scaling method. And this is so important because it shows that the strategy of scaling was the real game changer here, not just building a slightly smarter agent. So you might be wondering, does this amazing trick only work on one specific benchmark? Nope, not at all. The researchers immediately tested if this method could generalize to other places. And as you can see, the results totally hold up. On both Windows and Android benchmarks, just applying bBoN with only 3 parallel agents gave them a really nice performance boost. This is a big deal.
It proves the framework isn't some finely tuned thing for one environment. It's a broad strategy that works across different operating systems, which is exactly what you want for a tool that's going to be useful in the real world.
All right, let's zoom out for a second and talk about the big picture. Why is this so important? Well, this work is a huge step in turning AI agents from these fragile, kind of unpredictable toys into genuinely reliable tools that we can actually count on to get things done.
So, what are the main things to take away from all this? First, the simple idea of strength in numbers. Just using multiple agents is incredibly effective. It just works. Second, the real magic is judging what the agent did, not what the screen looked like. And those behavior narratives are the key that unlocks it all. This combination is what gets us so tantalizingly close to human-level reliability and gives us a practical blueprint for building the next generation of truly useful AI assistants. And I think the author's own conclusion just says it perfectly. They've found a practical, scalable, and effective way to improve real-world CUAs, which just stands for computer usage agents. This isn't just theory anymore. It's a real framework for building assistants that can actually work out here in the messy, real world.
Honestly, a breakthrough like this really makes you wonder. We just saw a massive leap in how reliable AIs can be for complex tasks. So the big question is, with frameworks like this leading the charge, how long is it going to be until an AI can truly and reliably handle all of our digital chores? The answer might be a lot sooner than we think.